All right? Is this a conservative vector field? All right, so I will tell you, if you calculate the curl of f, it's 0. It's true. Is this a conservative vector field, though? Right? I think I could do, how to find the potential energy. I would like to solve, partial u, partial x equals to y over x squared plus y squared. Yeah? Partial u, partial y equal to minus x over x squared plus y squared. All right? And partial u, partial z equals to minus z, right? I got to solve these. Must solve these to find my potential energy function u. Can we do that? Sure, we can do that. These actually have solution u of x, y, z equal to the inverse tangent of y over x plus some constant possibly of z, If you don't believe me, differentiate it, see what happens. What's the x derivative of this? Derivative inverse tangent is what? 1 over the thing, 1 plus the thing squared, right? Chain rule. So I have to multiply by minus y over x squared. That's the derivative of y over x with respect to x. Lo and behold, I do believe we have a minus y over x squared plus y squared, which is good. Except, oh man, what have I failed? What am I missing? What happens with the y derivative here? The derivative of the inside function is just 1 over x this time, yeah? Multiply that by x over x. Get x over x squared plus y squared. Now, it's not quite right? What am I missing? I'm missing a minus, right? I need to put a minus up here. All right, there we go. Now we're good. What should C1 of z's be, though? This right here tells you what? We should make our C1 of z maybe like minus 1/2 z squared. That ought to do it, right? So my potential energy as a function of x, y, and z, apparently, I can just do minus inverse tangent of y over x, right? Minus 1/2 z squared. There you go. But I've got bad news. This is not a conservative vector field. You're like, but you found a potential energy. You showed me the curl was 0. Why is it not a conservative vector field? All right. Let me make that sentence complete. This is not a conservative vector field on its domain. So unless we say otherwise, when we talk about conservative, we're talking about the domain of the vector field. And what's the domain of a vector field? What's our convention in math? When we're not talking about domain, our convention is that the domain is the greediest possible set that you can make that the thing is defined for, right? So what's the domain of this vector field? We better not have division by x squared plus y squared equals to 0. Where's that happen? The origin? Where else? this is, you could also call this R3 minus the z-axis, right? Minus the z-axis. We have to delete the z-axis. That's where x squared plus y squared is 0. Check this out. We can calculate the work done by this vector field around a loop that encircles the z-axis. Can I erase this business here? Okay. So if I want, here's my z-axis, right? I'm just going to look at like, maybe the unit circle should suffice, right? So the unit circle's got what? Like x equals to cos t, y equals to sine t, z equals to 0, right? So, and of course 0 less than or equal to t less than or equal to 2 pi. If I calculate the work done along c, in other words, the integral from 0 to 2 pi of like minus y dx plus x dy over x squared plus y squared, right? And understanding that I mean this subject to these conditions over here, right? So when we work that out, like what is dx? I guess I could just leave this as c for a second here. So that works out to 0 to 2 pi. What's my dx? What's my dy? Right? So minus y dx is minus sine squared, right? And x dy is minus, minus a minus. So I get sine squared plus cosine squared, I think, right? So I get sine squared plus cosine squared dt, right? By the way, we could have leveled this up. We could have done the circle of radius r here. Wouldn't have changed anything. Yeah? Because what happens? The r upstairs and the r downstairs, they'd be canceling, right? So you're just left with the integral of dt from 0 to 2 pi, which is, well, 2 pi. 2 pi is not equal to 0. If this was a conservative vector field, the integral around a loop in the domain has to be 0, but it's not. This is proof positive it's not a conservative vector field. If it was a conservative vector field, this could not happen. But it did. So this is not conservative. So you guys tell me the riddle. The seeming, like this is a paradox, right? Because it kind of seems like I've showed it's conservative because I showed you the curl was 0. I didn't show it to you, but trust me, it's true. 10 minutes of differentiation, we get to it eventually if you don't make a mistake. It's tough to see, but it's true. And it seems like I found a potential energy function, right? What's the domain of my potential energy function, though? That's more like the range, I suppose. But what the domain, there's something that can't happen here, right? Such that what? What is not allowed in that formula? X equal to 0 is definitely a problem. So we need x not equal to 0. Don't be deceived. This is only a potential energy function on, R3 either to the right or to the left of the x equals to 0 plane, right? So it's not a potential on the whole domain. That matters. Domain matters. And in fact, I think it's most natural when x is positive, truth be told, right? Do you know where this example comes from? What this is, guys, is the gradient of the angle function. Like this is essentially just the gradient of the angle function plus the vector 0, 0, z. That's all I did for this example. This right here is where this is coming from. This is why this is happening to us. We calculate the net change of the angle, the standard angle around the z-axis, we get 2 pi. It doesn't matter how far we are out, it's still 2 pi, right? You're like, can't you just use the angle function then for your potential energy, right? You can't do that though, because you can't define the angle function to be differentiable all the way around. There has to be a place where you jump from 0 to 2 pi, or from pi to minus pi. There's a place where there's a discontinuity of the angle, and if you had differentiability at that point, differentiability implies continuity, but you don't have continuity. So you simply cannot have differentiability all the way around for the angle function, no matter how you formulate the angle function. This is just one way, right? You could also use the inverse cotangent of x over y, and that would give you places where y is not equal to 0. You could choose still weirder angle functions, which lose like pi over 4 or something. That's where the angle jump is, all right? So it's a real issue, but this is all avoided in these sneaky weasel words over here, simply connected. That's what I was not talking about, and that's the whole issue. Simply connected means something. We need to have the domain of the vector field be able to deform like loops to a point in order to know that the curl being 0 implies conservative. This is a subtle issue, and it really is the thing which gave rise to the study of what's called topology. Topology is essentially the study of the shape of space. It's a way of counting holes or higher dimensional holes in spaces. And just now, recently, physics and engineering, like cutting edge physics and engineering, is starting to talk about topological models to things. It's one of the possible ways to look at big data. Maybe you can look at different large data sets and study their topology and find similarities in different data sets by comparing their topology, something like that. I looked at that a little bit when I was working for the Navy. Not very seriously, but there's something called topological data analysis, which really isn't much older than you guys, maybe not even that. So we're really at the genesis of these new mathematical tools. No one really knows quite what we're going to be able to do with them. Because the thing is, at this point in our technological existence, we have these stupidly large data sets, but no one really quite understands how to take those and understand them, right? So we need like better macroscopic descriptions of data set, and topology is one of those things that might be helpful. But anyway, it started by looking for the domain for conservative forces. Like the issue with domain is an issue of topology. And so anyway, math and physics are usually linked, and one feeds into the other. Okay, so Thursday we'll talk about how to do the phase plane diagram. So thanks, guys.